Problem number 2 is similar to one we did in notes yesterday. Small island is 2 miles from the nearest point P. So here's our island I. This is 2 miles. On the straight shoreline of a large lake, if a woman on the island can row a boat 3 miles per hour and can walk 4 miles per hour, where should where should the boat be landed in order to arrive at a town 10 miles down the shore from P in the least amount of time? So this is 10 miles. We want to figure out where should the boat land right here. So this is kind of like the oil well one where they were throwing the pipe underwater and above ground. So it's a similar setup. We are trying to find the least amount of time. So we're trying to minimize time. So we're going to have to write an equation for time. And this is one where it helps to kind of break it down, smaller parts first, easier setup, and just set up an equation in words. So we want to minimize the total time that this takes. So there are a couple different things that we have to take into account. We have to take into account the time it takes her to row the boat all the way to the shore. So we have time rowing. Plus, we have to take into account the time that she actually walks. All right, so break it down simple like this first before you start setting up any type of an equation. All right, now this is a little bit different. We're minimizing time instead of cost like the problem the other day. So time, we have to look at how do we figure out the time that it takes to do these two things? Well, that comes from a formula you guys should be familiar with. Distance equals rate times time. So this is how we generally see it a lot of times. Distance equals rate times time. Well, we're dealing with some distances here. We were given rates, how fast she's walking and rowing. We're trying to find time. So I'm going to solve this for t. So time is the same as the distance divided by the rate. So our total time here, I'm just going to keep this as capital T. Time rowing is going to be the distance rowing divided by the rate at which she rows. Plus the time walking is going to be the distance walked divided by the rate walking. All right, so these two things on the bottom, we know the rate at which she's rowing is 3 miles per hour. The rate at which she's walking is 4. So we can go ahead and fill those in right now. Parts we don't know are the distances. That we have to kind of come up with from the graph. And this part should be kind of similar to what we did the other day. We know that this distance right here from P to this point is going to be x. Right? We're going to set that as our x, which means this distance, the distance that she's going to end up walking, is going to be 10 minus x, because this whole length is 10. Subtracting that amount, we get 10 minus x. So that's going to be the distance walking is 10 minus x. So we can go ahead and put that on top of the 4. We need to figure out the distance rowing, and that we can use Pythagorean's theorem. So if we say this is z, this hypotenuse, then x squared plus 2 squared equals z squared using Pythagorean's theorem. So if we want to find out what z is, we have to take the square root of both sides. So this distance is going to be the square root of x squared plus 4. All right, that's our distance rowing. Square root of x squared plus 4. So that's going to go on top over here. All right, so the setting up, which can many times be the hardest part, is done. So we're going to have to take the derivative of this. But before we do that, let's kind of simplify what we're working with to make our derivative a little bit easier. We can write this as 1/3 times x squared plus 4 to the 1/2. Plus over here we can divide these. 10 divided by 4 is 5/2 minus 1/4 x. Right, so just taking each of these terms divided by 4. Now this is in a little bit nicer fashion for us to actually go ahead and take the derivative. So the derivative of the total time, we're going to bring that 1/2 out in front, so that's going to give us 1/6 times x squared plus 4 to the negative 1/2. We have to multiply by the derivative of the inside, so times 2x. Derivative of 5/2 is just 0. The derivative of negative 1/4 x is going to be negative 1/4. So we can simplify this a little bit right here. We get the 2 times the 1/6. That's going to simplify to 3. 2's cancel out. We end up with an x over 3 times the square root of x squared plus 4 minus 1/4. So from here, we want to figure out when that derivative is 0 or undefined. So it's not going to be undefined because this can't be equal to 0 down here, x squared plus 4. Not any real numbers at least. So what we're going to do is go ahead and set this equal to 0. Now at this point we could graph this function on our calculator and then find the 0. So if a calculator is allowed, feel free to do that. Set this equal to your y1, graph it, and then calculate the 0. But for now, I want to go ahead and actually solve this. So to solve this, I'm going to add the 1/4 to the other side. And now to get rid of these fractions, I'm going to go ahead and cross multiply. So 4x equals 3 times the square root of x squared plus 4. Divide both sides by 3 to get this square root by itself. So 4/3 x equals square root of x squared plus 4. Now to get rid of that square root, we can square both sides. We get 16/9 x equals x squared plus 4. Oops, this should be a 16/9 x squared. Now we want to get the x squareds to one side. So I'm going to go ahead and subtract x squared over here. And we end up with 7/9 x squared equals 4. We can multiply both sides by 9/7. So x squared equals 36 over 7. And then finally, we want to take the square root of both sides. So x equals 6 over square root of 7, or 6 square root of 7 over 7. But since we're doing a real life problem here, let's not leave that as a square root. This is approximately equal to, let's see, 2.267 for our x value. Now, we could go ahead and do a number line with our first derivative and figure this out, but we also, in this case, have kind of some endpoints we can check out as well. So we want to test and see what works for this one. Could it be maybe the quickest time if she rows directly to shore and then walks the rest of the way? So that would be the time if x is 0. Or could it be at our critical value here at 2.267? Or could it be that the fastest way is to row the boat directly to t? So that would be if x equals 10. So we want to substitute each one of these into the original function. All right, into our original function. You can do it into this one or this one. Those are still both the original function. If we put 0 in there, into there, we end up getting 3.17. If we put 2.267 in there, we get about 2.94. And if we put 10 in there, we get 3.4. So this does turn out to be our minimum time. And it is asking, let's see, where should the boat be landed? So it should be landed 2.267 miles from P. That's our final answer. Make sure that you go back and answer the question that they're asking.